guess it's about time to get going again.
Yep. We had our fun.
All right, we were going to talk about test methods for doing takeoff and landing tests. And one that's been used for a long time and still probably the simplest and inexpensive method is called the sighting bar. Actually, it consists of either one or two sighting bars located at a known distance from the runway. And here's kind of a picture of it. Okay, this is this sighting bar. You can either get by with one or two, and we'll explain what the difference is. But you have someone lining the airplane up down here at the starting point on the runway. Okay, they line the airplane up, and say this first sighting bar will measure the ground distance where he lifts off. And so what this thing does, you look through it and you have distance measurement, and it's all triangulation, okay? The known distance, so it's triangles, so you can figure how far down the runway it was when they lifted off. And through triangulation for altitude, if I follow that, usually we have some lines along the sighting bar, and when the airplane crosses that, that's the distance. And you track them. You've got some sort of little crank on the side of the sighting bar with a marker, and you just follow it along. And when he, either lifts off or crosses the 50-foot obstacle, you stop. You stop cranking. And then from that you can write down the distance wherever it occurred. In the two case, this guy would get the liftoff distance, and that would get the 1 to 50 feet. And you know where these things are located down the runway, and the site has to be essentially surveyed in for accuracy, but generally works fairly well. So it's dependent upon observers operating the sighting bar and upon a runway observer usually to confirm and particularly if you just use one sighting bar, usually you'll have somebody determining where the liftoff point is. So what you'll do is you'll track the airplane to 50 feet. When he crosses 50 feet, you'll get that distance, and then the person who was checking the liftoff back down the runway will go stand and mark where the liftoff point was, and then you'll crank back and see what the distance was that way, if you just use a single sighting bar. Nice thing about it, the raw data is immediately available, and it's possible to conduct more data runs and get a larger statistical sample. Another method which I've used some years ago, I don't know if anybody else is using it anymore, is called a strip camera. And it's similar to the sighting bar, except the method uses a strip camera which takes a picture of the airplane. It just takes a little strip of film, and you'll see the airplane on the film. You'll see the airplane going along the runway, every little picture of the airplane, and you follow it right up to 50 feet. It's kind of neat, and it has a time with it, so you can get that. And essentially, it takes at fixed intervals, takes a picture of the airplane and records it on a photographic plate. And then, problem with the method is that you have to, you don't have the data immediately. You got to go develop the photographic plate, but you do have a permanent record. And in many cases, that's kind of nice in this day of litigation, where there's a lot of lawyers running around out there who like to sue airplane companies, having real data to be able to show a jury, even though if the jury doesn't know what it means. You can still hold up your attorney can still hold up the picture, and, that tends to impress juries. But you still have to have runway observers to help you nail down exactly where the airplane lifted off and touched down in the case of landings. The next method is a movie theodolite, and it's similar to the strip camera, except that it's a movie camera. And you follow the airplane along. We used this when I worked at the beach, and you have a lot of movie film to look at. Somebody has to sit in a dark room and look at each one of the movie film and get data off of that film, or at least ever so often off of that film. In fact, we had a lady who did that for us, and if we did a takeoff and landing test, she would spend like 2 weeks in this dark room looking at this film. That's how difficult the data reduction was, and of course it took you that long to get your data back. However, it was, the nice thing about it was you could put flash bulbs on that would flash when the gear extended, so you knew when the liftoff was, or when the gear compressed in the landing test, the flash bulbs would go off, and so you knew which frame that it had actually occurred in, which was, a little more accurate. But like I say, it's more difficult to analyze. Here's a kind of a picture of it. You took these movies, and you had a stopwatch in the frame of film, and here's the airplane, and from that you can determine the height, and with those markers you knew how far down the runway the airplane was when this frame was taken, and that sort of thing. And movie camera was generally set up in the middle. You still had to line someone up. You had to generally communicate by radio with ready now for breaker release kind of thing, and so that because you had to start the stopwatch. All right, somebody had to start the stopwatch, so the crew had to tell when they released the brake so they could start the stopwatch. So, and you still had observers along the runway. Because number one, you need the rules require that you measure the wind and temperature at 6 feet above the runway and at 50 feet above the runway for the ground segment and the air segment, for those two segments. So you made temperature and also you had an altimeter involved in the whole thing because you needed to know what the pressure altitude was on the day you did the test. So that's the movie theodolite approach. A lot of the big airplane companies used an onboard theodolite so they could go, well, one of the requirements is in the rules now is that you have to test at high altitude. And a favorite place to do this is out in New Mexico, and it's at about 6,000 feet above sea level, so they don't have to extrapolate the data more than 6,000 feet. But nobody has a setup out there per se, and so a lot of airplanes or a lot of companies went to onboard theodolites onboard the airplane, and knowing how big the squares of concrete in the runway were, using the photogrammetric techniques, you can tell how high you are. And they would use that kind of thing. And of course, since it was on board the airplane, you didn't have any problems with time correlation. But again, kind of an expensive system for a test that you only do every so often. Another method is called the trisponder. It was developed by an outfit by the name of Del Norte Technology. I don't know if they're even still in business. But it was sort of a portable DME, or distance measuring equipment. And it came in a little box about yay big. And you could either set the box outside the runway or at the end of the runway and measure the distance to the airplane. You put a little reflector in the airplane, and this thing would ping on it and determine how far it was down the runway. Again, trouble was cost and complexity, because you had to coordinate. Plus, it did not, you either had to have two boxes in this case, or you had to have a radar altimeter tied in with this box in order to get height. So, you know, you're trying to get distance and height, and you have to know at the same time. In recent years, folks have tried to use GPS. The FAA will only accept a differential GPS, which is, of course, the most accurate one for doing this kind of testing. And we're in the process here. In fact, we have a student assigned. We're going to use a laser altimeter to coordinate with our lunchbox, as we call it, instrumentation system that goes in our Cherokee 6. Going to try to tie those two together to do use an onboard system for takeoff test. Well, you need to, in the procedure, you need to record the atmospheric variables, wind, outside air temperature, pressure, altitude for each run. And you have to get the wind direction and velocity, and temperature you would like, both at 50 feet and at 6 feet above the runway for each run. And you don't conduct these tests in winds in excess of 10 knots. Now that used to be our problem again when I worked at the beach, and we had to go 100 nautical miles up to Salina, Kansas to do the test, because out in the flatlands out there, the wind blows a lot. And so we would get up at 3 o'clock in the morning in Wichita, load everything on the airplane, fly up to Salina before the winds came up, or before the sun came up, because after the sun comes up, the winds come up, okay? To be up there and ready to test just when it got daylight, kind of thing. And many days it was get up, go out, load the airplane, fly to Salina, winds come up, get back on the airplane, fly back to Wichita to do it again tomorrow. You know, one of those kinds of things. So again, that becomes a problem. The 10 knot wind limitation. There's enough, essentially enough variables in it without introducing another one of high winds. Well, a few points to go along with it on takeoff. To reduce the data scatter, the airplane should be stopped at the starting point. Pilot holds the brakes, bring the power all the way up, and then allow the power to stabilize, give the ready now for brake release so everything can be coordinated, and release the brakes. Before he releases the brakes, however, he should attempt to use the same technique for each takeoff. Determine the optimum technique prior to getting any data, do all the practicing ahead of time. This is such an involved test that it's a good idea for the pilot to do all these practice runs ahead of actually data collection. And then we'd like to collect data during the entire takeoff run and climb to the obstacle, but, on some automatic device. But if you can't, then you need to get the data just prior to brake release, at liftoff, and at the 50-foot obstacle height. So if you're using something like a sighting bar, that's what you do. Landing, of course, the takeoff procedure sort of applies in reverse. Again, we talked about this before lunch, but the residual power shouldn't remain on the airplane after touchdown. And you apply braking to the maximum without skidding the tires. Now, many airplanes have anti-skid, or particular more expensive airplanes have anti-skid on the brakes, which is good because then the pilot can just, get on the brakes and the anti-skid takes care of not letting the tire skid. But on small airplanes, you're probably going to blow some tires, or at least skid flat spots on them, and need to change tires during these tests. But you want to get the maximum braking without skidding the tires. And you want them to cool between runs. Again, my technique has always been just to, if it's a retractable gear airplane, leave the gear out during the circuit around the pattern to help cool the brakes. Try to be as consistent as you can because it's going to make a pretty big difference in the ground distance. We talked about this too, but at the end of the landing run, stop the airplane and sit there for a while. That way, the day, you can see in the data system, if it's an onboard system, that the airplane has in fact stopped at this distance. If it's, the photo system, one of the photo systems we talked about, if you don't stop and sit there for a while, you'll miss that. In reducing the data, you'll miss that point where the airplane stopped. Here's some data. This was done with that DMU unit. So we have time on this axis. And we got 3 or 4 things on here. Here's velocity. Okay, and this is a takeoff. So we can see the airplane, accelerate and then try to hold the speed here during the climb portion. Here is the altitude. Here he's on the ground, lifts off, climbs to the obstacle, okay? And here is the distance track. So that's the kind of thing that you would like to get because then you can integrate those curves to determine distance and acceleration and those sorts of things. Here's a landing. We can see, okay, he's altitude here. This is velocity, so he's on speed. He touches down here. Velocity starts to come down. Here is altitude. Altitude comes down, lands here, looks like he bounced. And goes on there, okay? And then the distance is that track there. So that's data reduction. Well, for takeoff, we make a wind correction first, and the wind correction for the ground distance is the first equation. So this is the observed distance that we got off of, we'll say, one of those plots that we just looked at. Top is the velocity of the wind, and the one below it is the takeoff velocity that you observed in those wind conditions, okay? So that's the ground distance. The air distance is just the observed air distance times the velocity of the wind, and of course the wind velocity may be changing. That's why we get it at 6 feet and at 50 feet to try to integrate it over that distance. So the velocity of the wind times the time that the wind had to act on it to the 50 feet. So that's the wind correction for the takeoff. For the reduction to standard day conditions, Here's the equations for a jet airplane. Notice this is the test thrust, the standard value of thrust. Root sigma, test value, what the standard value is. Weight, standard weight, test weight. Notice those powers that these things are raised to. And you say, wait a minute, why are they 1.6 or 2.3? Why wouldn't they just be squared or square roots or that sort of thing? Well, these equations were developed empirically from doing a lot of tests. Here's for a propeller-driven airplane with constant speed like the Cherokee 6. Notice that we have RPM, in addition to horsepower, we have RPM in there. The test and the standard value. So, you know, we use, say, 2,700 RPM as a standard value. Well, you would record whatever the test RPM in case it was different. You know, normally if they were the same, that'd be 1. And so both the ground and the air distance. And normally those weight corrections would be squared values, but it's turned out that empirical equations have found that it's better that it be raised to the 2.6 power. Landing, since we don't use power for the equations for landing are a good deal simpler. Here's a plot of takeoff distance. I think this is for a Piper Navajo. I think that's where I stole this plot. Notice that this is correction for temperature. This is weight. Notice that its distance is farther as with the heaviest weight, and then it decreases. This is for a headwind. Some people plot a tailwind on here, and in that case, these things would go this way. So this is what you're trying to get with those equations. You're trying to get to a chart the pilot can use for takeoff distance. Landing equations, again, wind correction values look a good deal like they did for takeoff, except they're kind of reversed for the landing